Hi everyone, welcome back to Cody's Lab. So today I'm going to be making a cryogenic thermometer, and I'm going to be doing this using two different sizes of copper wire and a digital multimeter. Also some things to put them together. But the idea here is that the copper metal, or actually most metals, as you cool them off or warm them up, the electrical resistance changes proportionally to the temperature change. So you can take this multimeter, hook it up to a coil of wire, figure out its resistance, and then plunge it into your substance you want to check. The resistance will change as the temperature changes, and then you can calculate based off of some reference points and the general curve of the resistance change of the metal, and you'll be able to figure out the temperature. So this is just some copper wire. I think it's about 20 gauge or so. I'm just going to take a chunk of this about yay long, and this is just to hook my terminals of the multimeter to. The idea here is that the resistance in this part is going to be basically negligible. Now this is some copper wire. It's incredibly thin. In fact, it's a 42 gauge copper wire. And this way I can have a lot of resistance with a fairly small coil. I'm looking for a resistance of something like 100 ohms. It doesn't have to be exactly that, but that's what I'm shooting for. And given how thin this is, that shouldn't be very much bulk. Okay, so let's see if I can just solder this thin wire onto the thick wire. That should do it. Of course, that was entirely out of focus. And wind this wire up on here until I got a nice big ball of wire. This could take a while, so I'm going to listen to a lecture on my phone, and I'll see you guys. Okay, so there's my coil of wire. You can see it's still fairly small. That's good because the heat will be able to transfer into it very well, and out of it is just the same. Alright, let's see what kind of resistance we got in that little coil there. 96 ohms? So close to 100. I'm going to call that good. So, now let's package this thing up, make it look a little prettier. Okay, so this is a little annoying. So we got about 60 ohms there, but if I give this coil a little bit of a squeeze, then the ohms change. I've added a glass tube to this. This way I can wrap it faster and more evenly, and I can keep these two ends apart from each other. Okay, so there's the new coil. I'm just going to do a quick check on the resistance here. There we go, just over 100 ohms. Perfect. Now let's plunge it in liquid nitrogen and see what happens. Okay. Wow, look at that. The resistance dropped way down to 13. So, now if I were to put this in an unknown area, and that goes down to 13 ohms, then we'll know that I reached liquid nitrogen temperatures. And see now as it's warming up, the resistance is increasing. It's a thermometer! So I want to protect that coil of copper a little bit, so I'm going to wrap this gas-resistant Teflon tape around the copper just to protect it a little bit better. This also chemically protected, which is good. You check with ice water, see what effect that does on it. Looks like we've stabilized at about 97.8 ohms. There we go. That's a decrease of over 10% off of the original temperature at the 28 degree ambient. Alright. So here it is at 61.4 ohms. And I've got some dry ice in there, as you can see. Now for my next trick, I'm going to get a temperature reading from something colder than liquid nitrogen. That is, solid nitrogen. And to do that, I'm going to have to put this in a vacuum chamber. You may also notice that I've replaced some of the tape on this. The electrical tape didn't seem to really play well with the cold temperatures, but the Teflon tape seemed to do it. So it's in the nitrogen and holding steady at 12.7 ohms. Let's close the chamber and fire up the vacuum pump. As you can see, the nitrogen will begin to boil, quite profusely actually, and the temperature will drop as the boiling gas carries away some of the heat. Already down around 10 ohms, 8.6. Looks like we're about to freeze. There it is, it froze. Looks like it was 8.0 at the time. It seems to be holding steady at 8.0. Oh, yeah, okay. So there it is, the triple point of nitrogen. And that should hold steady at that point for a little while, and then it'll begin dropping again as the nitrogen starts to sublimate and carry away even more heat. The gas is really expanding as it comes off that. See those wispy geysers? Temperature's increasing. That's interesting. You know what I bet it is? Nitrogen has evaporated away from the thing because the thermometer will be producing a small amount of heat. Yeah, I can see the nitrogen is like boiled away from the sides of it. So yeah, it's just going to get hotter now. It's not conducting its temperature away as efficiently, even though the nitrogen might actually be getting colder. Oh well, I guess we'll stop it there then. Alright, let's let the air back in, see what happens. See, the nitrogen melted? Didn't completely melt though. Okay, let's open this up. See what we got. You know, maybe if this was insulated enough. Oh, look at that, we still have slush. I just touched solid nitrogen. Bet nobody else can say they've done that. Or at least, nobody else on YouTube. Let's see. That's a little cold. Last thing I'm going to do today is some liquid propane. So, just take a little bolt like this, some pliers, turn this upside down. Nobody light a match. Okay, let's see what resistance this gives us. Looks like 74.4.3, somewhere around there. You know what? Let's put this thing in the vacuum chamber and see how far it goes down, because this will boil just like the nitrogen did, and it should lose temperature, and then we can see how much, how cold we can get this. Probably won't be able to freeze propane because its triple point is down in the like 10 to the -6 atmospheres, so I don't think I can get to that point today. But we should be able to get quite cold with it. There we go. It's boiling. I got the gas vented to the outside, by the way, so. And this pump is fairly good with flammable materials. I still wouldn't recommend pumping stuff like this, but I've decided it's safe enough for my tastes. I start to notice that the bubbles start to get really large. So we're down below the temperature of dry ice. It's still boiling away. We're about 51.7. You see the propane's boiling away. We've lost quite a lot of it. You might be able to see that piece of paper I dropped in there. Yeah, I'm using some paper as a boiling stone. And there it goes. Still dropping in temperature, or in this case I'm measuring the resistance. Alright, looks like 47.9 is as cold as I can get. The propane's still in there boiling, but the pump's getting really hot, so I might have to shut her down. Okay, so I don't have screen recording software on this computer, so I'm going to have to use my camera. But I've got my data here in a spreadsheet. I've just got a placeholder for this number for the temperature, but all these others should be the actual temperature that the things were at this pressure. And you can see this graph over here. Now I could just take a like a line through these points. They are mostly linear. I could just take like a linear regression right there, and you could put this point in at about 160 Kelvin. But this line is not actually linear. It actually has a curve to it. You look down here, you see the liquid nitrogen and solid nitrogen, the ohms per Kelvin are not the same as the other numbers. See the other points? In fact, the propane and the dry ice is a little bit less than the say the water and room temperature. That's because this is a curve. It doesn't go straight down to 0 ohms at 30 Kelvin. It actually kind of curves off and it never reaches 0 because copper is not a superconductor. In fact, if I look over here, so this is about what the curve should look like. See up here at the higher temperatures it is pretty linear, but you get down to the really cold temperatures and it starts to curve away. If we look at this, you try to fit this piece of paper to it, you'll notice I can't really fit all the points on these lines. In fact, these groupings of points here kind of seem to fit on their own lines. So what I can do is just take this number between those two and get a pretty good approximation of where this point should go. I mean, it's probably only off by a few degrees, really, and I think that's pretty good. Most digital thermometers work about the same way as mine, but only the very expensive ones actually take into account the whole curve. So it's actually pretty cool for a homemade thing. Anyway, hope you enjoyed. I'll see you next time.